A tower crane rises above a city, 200 feet of steel, 540,000 pounds of concrete beneath its feet, hundreds of tons balanced overhead. Yet every instinct says it should fall. The question at the heart of "it moves," the engineering that keeps tower cranes standing, is simple. Why don't they? In July 2009, a single shortcut at Liverpool's King's Dock Mill hurled a crane and its operator into disaster, exposing how the invisible foundation decides life or death. What secrets hide in the ground beneath these giants, and how close have we come to catastrophe? Stability for a tower crane begins with the ground beneath it. Each crane stands on a reinforced concrete pad measuring 30 feet by 30 feet and 4 feet thick, an immense mass weighing over 540,000 pounds. This foundation is not just a block of concrete. It is engineered to resist overturning forces from the crane's towering mast and sweeping jib. Before any steel rises, engineers specify the concrete's strength and set a strict timeline for testing. The so-called 70 in 7 rule governs the process. After 7 days, the concrete must reach at least 70% of its final strength. Full strength, 100%, arrives only after 28 days. To verify this, crews cast test cylinders from the same batch of concrete used for the pad. These cylinders are crushed in a compression machine at 7, 14, and 28 days, with results recorded and reviewed. The numbers matter. If the concrete does not meet its strength targets, the crane cannot be erected. Anchor bolts embedded in the pad are just as critical. Each bolt must achieve a minimum of 4,000 pounds per square inch before it is considered safe for use. On some sites, especially where bedrock lies deep below, engineers drill steel anchors 20 to 50 feet down, locking the crane's base directly to solid rock. Every step, from mixing concrete to torquing bolts, is documented and signed off by licensed professionals. The process is methodical and unhurried because patience is the price of safety. Only when every test passes, every bolt holds, and every record is verified does the crane begin its climb into the skyline. On July 6, 2009, the quiet of King's Dock Mill in Liverpool was shattered by a deep, rolling rumble. A tower crane, nearly 260 feet tall, pulled free from its base and crashed backward onto the apartments below. At the heart of the collapse was a hidden shortcut. 4 steel dowels, each 20 millimeters thick, had been used instead of the heavy-duty reinforcement bars specified in the engineering plans. This substitution, meant to ease installation, left the foundation fatally weakened. Crane operator Ian Gilham, a father of 4, was inside the cab when the structure gave way. He was hurled nearly 200 feet, landing amid twisted steel and shattered concrete. Gilham survived, but the injuries were devastating. Permanent paralysis, a fractured skull, broken ribs, and severe spinal trauma. He would later receive a £2.7 million settlement, yet the accident erased his memory of the day and ended his career. The aftermath was chaotic. 56 tons of counterweight crashed through the roof of a neighboring apartment, scattering debris and forcing a mass evacuation. Residents described hearing a thunderous roar as the crane wrenched itself free, the inadequate dowels shearing apart under forces they were never designed to withstand. No bystanders lost their lives, but the physical destruction and psychological toll lingered long after the dust settled. Investigators traced the failure to a series of missed checks and unauthorized changes. The engineering firm's design had not been independently reviewed, and site crews altered reinforcement without reapproval. The health and safety executive prosecuted both the contractor and the designer, exposing a chain of oversights that allowed a critical safety margin to vanish. In response, new regulations mandated independent engineering checks, rigorous material certification, and full documentation before any crane is erected. The lessons from Liverpool reverberate through every foundation poured today, a stark reminder that even a single shortcut can carry consequences measured in lives forever changed. Balance is the silent force that keeps a tower crane upright. At the heart of this balance are the counterweights, massive concrete blocks mounted on the counterjib, opposite the working arm that lifts heavy loads. Each block measures 4.5 meters in length and weighs 25.3 tons, about as much as a fully loaded city bus. On a large crane, engineers stack as many as 32 blocks, building up to 400 tons of ballast. These are not simply placed. Each block interlocks with the next, forming a rigid mass that cannot shift or slide, even as the crane slews and tilts under load. The principle is straightforward, but unforgiving. Every time the crane lifts a load, the force it creates tries to tip the crane forward. Engineers counteract this with a moment, force multiplied by distance, created by the counterweights on the opposite side. For example, a 10-ton load suspended 40 feet from the mast generates a 400-foot-ton overturning moment. The counterweights must generate an equal and opposite moment to keep the crane in equilibrium. If the numbers do not match exactly, the risk of tipping becomes immediate and real. Precision is non-negotiable. Before a crane is put to work, engineers calculate the required ballast using the moment formula and double-check every block's weight and placement. At fabrication facilities, each counterweight is weighed and measured, then marked for verification on site. Field crews confirm every block's identification and position during assembly. A single miscalculation or a block out of place can compromise the entire structure. This system, though robust, has its limits. The counterweights are designed to balance the maximum rated load under normal conditions. But when winds increase, or when an operator pushes the crane to its limits, the safety margin narrows. The next chapter in crane safety explores what happens when those limits are exceeded. On July 14, 1999, the Miller Park construction site in Milwaukee was dominated by the presence of Big Blue, a Lamson LTL 1500 crane with a 340-foot boom, a 200-foot jib, and a total weight of 2,100 tons. That afternoon, crews prepared to lift a 510-ton steel roof panel, a curved structure larger than a tennis court. Winds at ground level hovered between 22 and 24 miles per hour, with gusts climbing as high as 34. Ironworkers voiced their concerns and left the site at noon, refusing to risk their lives in conditions that exceeded the Krausen's 20 miles per hour wind rating. Despite these warnings, management pressed ahead with the lift. As the roof panel rose, its curved surface acted like a giant sail. Meteorological data from local weather stations confirmed that wind gusts at elevation were not only sustained, but unpredictable, amplifying the lateral load on both the crane and the suspended panel. Calculations after the fact revealed that the wind imposed forces up to 250% higher than the crane's design could withstand. The kingpin, a critical steel pivot at the heart of Big Blue's rotating mechanism, developed radial fractures under the relentless stress. Within seconds, the entire structure buckled and collapsed. 3 ironworkers, Jeffrey Wisher, William DeGrave, and Jerome Starr, were killed instantly. An OSHA inspector, present to document the lift, captured the disaster on video, providing investigators with a real-time record of the sequence of failure. In the aftermath, attention turned to the digital records. The onboard Mitsubishi computer, which logged wind speeds and lift data, was found to have had its files deleted minutes after the collapse. The missing data fueled controversy, raising questions about accountability and transparency in the decision-making process that day. The collapse of Big Blue stands as a stark lesson in the interplay between engineering limits and human judgment. When environmental forces exceed design parameters and warnings are ignored, even the most massive machines can fail in moments. The events at Miller Park reshaped industry practice, embedding wind load analysis and stop work authority deep into the DNA of modern crane operations. Tower cranes soar hundreds of feet above city skylines, yet their slender frames are anything but fragile. The secret lies in the steel that forms each mast. Engineers rely on ASTM A572 Grade 50 steel, a high-strength alloy with a minimum yield strength of 50,000 pounds per square inch and a tensile strength of 65,000 psi. To put that in perspective, a single 1-inch thick bar of this steel could suspend the weight of 10 Ford F-150 trucks before showing any sign of permanent bend. But strength is only part of the story. The lattice mast, built from a network of interconnected triangles, transforms raw steel into a structure that is both lightweight and incredibly rigid. Each triangle distributes forces along its sides, preventing the mast from buckling or twisting under load. This geometry allows the crane to reach skyward without adding unnecessary weight, and it ensures that the structure can absorb and redirect the immense forces it encounters every day. Flexibility is engineered into the design. Rather than resisting every gust of wind, the mast is built to sway, much like a tall tree in a storm. This controlled movement dissipates the energy of wind and shifting loads, reducing the risk of fracture. At night, many cranes enter what's called weather vane mode, with the jib rotating freely to align with the wind, minimizing stress on the entire structure. The ability to sway, rather than snap, is what lets these towers endure the unpredictable forces of the modern construction site. March 15, 2008. On the 18th floor of a Manhattan construction site, 6 workers were installing a tie-in collar, a steel ring weighing 11,200 pounds, meant to anchor the crane's mast to the building. Lacking a mobile crane, the crew used the tower crane itself to hoist the collar, temporarily suspending it with 4 polyester slings looped in a V-shaped choke around the mast legs. The slings, rated for 20,000 pounds in a straight lift, lost most of their strength in this configuration. With the V-choke, their safe working limit dropped to just 7,100 pounds each, well below the collar's weight. As the load hung in place, workers heard 3 sharp popping sounds. In that instant, the slings began to fail, one after another. The collar slid 9 stories down the mast, striking a lower collar and shearing through the tie beams. Both fell to the 3rd floor, leaving the crane mast above unsupported. The entire structure toppled, killing 7 people, 6 workers and a civilian on the street below. Investigators turned to Fritz Laboratory at Lehigh University, which recreated the failure using identical slings and geometry. Their tests produced the same 3 popping sounds, confirming the sequence of sling rupture. The disaster exposed the hidden danger of misunderstood rigging geometry. When a sling is choked around a sharp angle, its capacity can drop by 2/3, a fact that proved fatal that day. Every bolt holding a tower crane together carries a burden measured in lives. Each connection is tightened to a precise value, verified not by guesswork, but by ISO-calibrated torque wrenches. Manufacturers specify exact settings, often 900 to 1,400 Newton-meters for the largest bolts, and every fastener must be checked again 3 to 6 weeks after installation. This interval allows for the subtle settling that comes as steel stretches and compresses under the crane's constant motion. If bolts are missed, the consequences can be deadly. On May 30, 2008, a Favco tower crane in Manhattan suffered a catastrophic failure. The operator's cab and turntable tore free from the mast, plunging to the ground and killing 2 workers. Investigators found 30 loose bolts at the failed connection, 9 of them sheared completely, The inspection logs revealed a missing record of the mandatory retorque check, but the failures went deeper than maintenance. The turntable assembly had been supplied by RTR Bearings, a company in China whose bid came in at just 18% of the cost quoted by a domestic supplier. Their welds did not meet American standards. Radiographic tests flagged flaws a month before the collapse, but warnings were ignored. In testimony, the father of one victim said, "My son was killed for one reason only: greed." The lesson is clear. Every shortcut, whether in torque or procurement, puts lives at risk. Routine checks and honest sourcing are not optional. They are the last line of defense. Above 265 feet, a tower crane cannot rely on its foundation alone. Wind and weight create powerful bending forces at the base, threatening stability as the mast rises. To counter this, engineers install tie-in systems at intervals of 80 to 100 feet. Each tie-in uses a steel collar that wraps around the crane's four mast legs. Heavy W12 by 79 steel beams extend from these collars, anchoring the crane directly to the building's structural core. This assembly transfers lateral loads, sideways forces from wind and movement, into the much stiffer building frame. By sharing loads between crane and building, the system prevents dangerous swaying or collapse. The ability to tie into the structure is what makes modern skyscraper construction possible, allowing cranes to climb hundreds of feet higher while maintaining safety and control. Electronic safety systems now stand guard over every tower crane, watching for threats invisible to the human eye. Load moment indicators, known as LMIs, combine sensors that measure the crane's jib angle, the weight of each load, and the distance from mast to hook. These values feed into a microprocessor that calculates overturning risk in real time. If the crane approaches its safe limit, the LMI intervenes, locking out controls before stability is compromised. Wind sensors, or anemometers, work alongside these systems, halting operations automatically if gusts reach 45 miles per hour. In January 2009, a Patane crane atop a Chicago high-rise developed a hidden crack in one mast leg. The warning came as a sudden popping sound, but it was the electronic monitoring that prompted an immediate shutdown. The crane stood on 3 legs for days, proof that when sensors and alarms work as intended, disaster can be stopped before it starts. Today's anti-collision systems fuse GPS, LiDAR, and radar, detecting obstacles with millimeter precision and adding another layer of vigilance to the skyline. Alvaro Becerra's day begins in darkness. By 3:30 a.m., he's already climbing the tower for his daily inspection, moving rung by rung through the steel framework. Inside the cab, he checks every system: 180 degrees of glass for visibility, an ergonomic seat, and monitors that cut through blind spots. Above him, the crane's mast and jib form a lightning rod, channeling any strike safely through the structure. The cab itself acts as a Faraday cage, shielding the operator from electrical surges. Beneath the crane, copper grounding cables run to earth, tested to ensure resistance never exceeds 4 ohms. Once the crane rises above 200 feet, red obstruction lights blink through the night, visible 3 nautical miles away, an unspoken language to pilots overhead. Rules like these are not just codes on paper. They shape every hour of Becerra's routine, from pre-dawn climbs to final system checks. In his words, safety is the line between going home and becoming a statistic. Yet even with discipline and vigilance, the patchwork of local and federal licensing creates gaps that only experience and ethics can fill. Every safeguard, every regulation is written in the memory of those who paid the ultimate price. A single tower crane can weigh over 500,000 pounds and soar above 65 stories, yet its stability depends on precise engineering, down to every bolt, tie-in, and concrete test. As this documentary has shown, failures at Liverpool in 2009, Milwaukee in 1999, and New York in 2008 each resulted from specific lapses: inadequate foundations, ignored wind limits, or overlooked connection details. These tragedies led to new standards: rigorous foundation testing, ISO-verified bolt torque, and sensors that halt operations in unsafe winds. Yet some questions remain, such as why key wind data from Big Blue was deleted, or how fragmented regulations still allow gaps in oversight. Today, every crane that rises over a city reflects hard-earned lessons, reinforced by daily inspections and evolving safety codes. The evidence is clear. Each rule and safeguard is written in response to past loss. Tower cranes stand not because they defy physics, but because engineering, vigilance, and memory keep them upright.